Hello students, welcome back. Let us resume our discussion in section 3, and I hope this time is really final. This is another optional video, and we are going to continue over to higher dimensional case. We just did this one. We can find inverse matrix through elementary row operation, major pain in the rear end for humans, but piece of cake for computers. And consequently, we get a unique solution. We went through that kind of example. And of course, we can create similar problem for much bigger system, like 10 by 10 or even 100 by 100. But in some other cases, the inverse does not exist. And this is one of those examples. Let's see, do we have the same matrix here? Oh yeah, we have the same matrix. So this is 1, -2, 4, 4, 3, 81. So is this the same matrix? Please check. 3, 1, 3, 1, -2, 4, 4, 3, -1. Okay, all right. What is the determinant of this? Determinant is 20. And then if I take mod 15, oh, wait a minute. What am I thinking? Determinant of A is 20, and a 20 and 15 are not relatively prime. That's clear. That much is clear. All right. So in this case, determinant is not relatively prime with this modulus. Therefore, this matrix is not going to be invertible, modulo 15. So the elementary row operation method will not be fruitful. As a matter of fact, it'll work out, to tell the truth. Instead of an inverse matrix, you're going to get what do you call the row-reduced echelon matrix, and with appropriate pivot, and you can find out algorithmically. But oh, that's going really deeply into linear algebra, computational linear algebra, and certainly that's not what I'm up to. So let's just stick to the usual method. Let's use the usual elimination method. So let's eliminate x. So with 3x here, 4x there, and we have just x in the second line. So we use the second lines to remove x from the first and third. How do you do that? Multiply 3 to the second line and subtract from the first line. That's going to remove the x term in the first line. And multiply 4 to the second line and subtract it from the third line. That's going to remove this 4x. So multiply and then subtract. If you do that, you're going to get the first line and third line like this. And then a little bit of simplification, mod 15. This 11 and -17 are a bit too big, so I can simplify a bit further into the final form here. Now, let's not worry too much about the second line for the time being. And let's look at the first line and third line. We have y and z only. So we have two equations and two unknown variables. Yeah, we can solve that. Or can we? Well, we are doing congruences, not equations, so things are going to be a little bit tougher. Please expect that. Okay, let's apply the same type of method. Let's eliminate y. So multiply 4 to the first line, multiply 7 to the third line. That's what you're going to get. 28y will be in common. And then add them up, that'll kill off this 28y and -28y. Here's the end result. -50z is -55, mod 15. We had some big number computations, but those are all elementary, so please believe me. Now up to here, once you got that, it is tempting to simplify this, divide by -5, and get 10z is 11. Like this. Yeah, from here, divide by -5, and get this simplification. Does it work? No, it doesn't. It does not work. I cannot freely divide by -5 because -5 is not relatively prime to 15. -5, which is congruent to 10, and that's not relatively prime to 15. So we can't do this. What can we do? We can divide -5 to this one as well. Here's the correct computation. Divide by -5, divided by -5, mod 15, that too you have to divide by -5. Shouldn't it be mod -3? That's same as just mod 3. So 10z, well, 9 is congruent to 0, mod 3. So that's just c. 11 is congruent to 2, so you get the solution easily. So here, after this, divide by 5. Dividing 5, simplify, and dividing 5 also to mod 15, coming down to mod 3. If you're a little uncomfortable with this division, here's a proof. What do you mean by congruence modulo m? The difference is divisible by 15, right? So difference is 15k. Now in this equation, now this is an equation, right? Really, this is equality, not congruence anymore. Divide each by 5. Divide each by -5, excuse me. Then positive 10, -11, and -3, or 3 times -k. So mod 3 versus mod -3, there's no difference. I can always, adjust this some integer k into some other integer -k. So division by 5, that works perfect to moduli as well. So we have z is congruent to 2. Is that a unique solution? It's a solution, but it's not a unique solution. Because, z is running from 0 to 14. You're doing mod 15. But z is 2 mod 3. That works only up to 0, 1, and 2. Up to 0 to 2 only. So you have to extend it over to 0 to 15. You're going to get 2, 5, 8, 11, and 14. All those have remainder 2 when you divide by 3. So they belong to the same remainder class as 2 mod 3. And then we have to do this computation mod 15. So extend this up to 15. And then what if you extend further than 15? Will that cause any other trouble? No, it won't, because 3 divide 15. The same pattern will just repeat. And the detailed proof is left to the students. In the end, you get z is 2, 5, 8, 11, or 14. Okay, we got z. So use these, substitute all these to find out y. You can do that either the first equation here or the third equation there if you want. Either way, it'll work out. Elementary but tedious. You can find y values for each of these z's. And then now that we have y and z, go back to the original and then get the second equation involved now to find out x values. So from z values, 1, 2, 3, 4, 5 values here, we get y values, again 5 values, and then those y comma z, those 5 pairs, you can find x values. So total, there are 5 triples. You're getting these numbers if you do all those computations. Elementary, easy, but tedious. So z values 2, 5, 8, 11, and 14. And then from those, we get y values. And then y and z values, we get x values. Just substitution technique. And then here is Mathematicus verification. I just wrote a program that's test everything by brute force. So there are 15 numbers, so 15 by 15 by 15. So 3,375 triples to consider and calculate them all, and which one fits. So the equation, left-hand side -1, left-hand side -2, left-hand side -3, and then checking if all those are 0 modulo 15. That's what I'm checking. And then you can check for 3,300 and whatever. Yeah, 3,375 triples to calculate, and then check them all, and then we get the solution set. For computers, it's a piece of cake. You see, it's that quick. So we can use the usual elimination and substitution methods to solve in any case, but those tends to rely too heavily upon human work. So you can reduce those into elementary row operations and stuff so that you can use computers more effectively. But that's going a bit too deeply into computational linear algebra, so let's just stop there. And that's how the systems of linear congruences work out.